In this lesson, we're going to talk about pressures, refrigerants, and the refrigeration cycles, as well as some of the major components of the refrigeration cycle and systems. A refrigerant is a chemical mixture that's designed to boil at certain temperatures at a certain pressure. A refrigerant is designed to move large quantities of heat from a place we don't want it to a place we do. In other words, we need a substance that can move a tremendous amount of heat, more than water, per pound, from, let's say, inside a cooler where we don't want it to outside a building where we want it. Now, refrigerants also have to have some additional components. A refrigerant will never be used up. In other words, it should go round and round in the refrigeration cycle, and unless there's a leak, you should never have to replace it. A refrigerant should be non-toxic and non-flammable. A refrigerant should also be environmentally friendly. Okay, and so all of this is a tall order. So we have certain chemicals that are used in certain places, and these are refrigerants. Refrigerants all work on the temperature-pressure relationship. In other words, with water at atmospheric pressure, it boils at 212 degrees. If the pressure drops, the boiling point will drop as well, for example, at higher altitudes. Refrigerants all have specified boiling points at atmospheric pressure, and then that changes based on the different pressures. For example, R134A, which is what the refrigerant used in cars, at 0 psig will boil at negative 14 degrees Fahrenheit. R12 at 0 psig has a boiling point of negative 20 degrees Fahrenheit. So knowing the boiling point at 0, a chart can be created to show the boiling points at other pressures. This chart is called the temperature pressure chart, or TP chart. So when you're looking at a TP chart, find the column, for example, for 502, locate the 0 psig on the column, look to the left, and find the temperature that this refrigerant is boiling at. R502 boils at negative 50 degrees. So again, let's look at R410A on this chart. We want to find as close as we can get to 0. So that's going to be 3.5, okay, because the chart doesn't go any lower than that. You look at the R410A column, 3.5 is your top number. Go to the left to the temperature column. This is negative 50 degrees. Can do the same thing with R134A. Find the number closest to 0, so that's going to be 0.1. Okay, that's actually vacuum. In this chart, the darker numbers are vacuum. Go to the left, and you'll find negative 15 degrees. R134A boils at negative 15 degrees. Most systems do not need to run at temperatures this cold, so the pressures are increased by the use of the compressor, which makes the boiling point increase. In other words, and most of the time, we don't want to run refrigeration systems at 0. There's a couple different refrigerants classifications. For example, CFCs. Okay, they can contain chlorine. They're called chlorofluorocarbons. They're old refrigerants, and at this point they've been phased out. You may still come across them in equipment, but it's very tough to buy new CFCs. HCFCs, hydrochlorofluorocarbons, they're a little bit more environmentally friendly because they've added some hydrogen rather than the chlorine. You'll find that it's R22 and a couple other refrigerants that you'll find in a lot of the residential systems out there. Again, HCFCs are being phased out. You can no longer buy new equipment with HCFCs in them. HFCs are hydrofluorocarbons. They're newer refrigerants. They don't damage the ozone layer. And you'll find this in most of the newer residential and commercial units. Refrigerants such as R134A, R410A, they're all HFCs. Now, along with the refrigerants, you have refrigeration oil. They provide the lubrication for the compressors. They're mixed into the system. They're going to go around with the refrigerant. And they will eventually make it back to the compressor, work its way through the compressor, and again go through the cycle. You have polyester oil, alkylbenzene oil. These are synthetic oils. Refrigerants come in different color-coded containers. You must know the colors for R22, R134A, R410A, R409A, and R502 as well as R12. The oils used are specific for the type of refrigerants. Don't use the wrong oil with the refrigerant. Make sure you know what you're supposed to be using. Some oils don't do very well. If you look at this picture, you're going to notice that there's a lot of different color refrigerant cylinders out here. Each cylinder is color coded with a specific color for that refrigerant. For example, R22 is green. R12 is sort of a white. R134A is a light blue. R500 is yellow. R404A is sort of a rust-colored orange. And R502 is sort of a lavender or pinkish color. This chart, as well as the one in your book, will show you exactly what the cylinder colors are, the chemical names for the refrigerants. Again, don't worry about them all because you'll always have a chart you can look them up on. Now, the refrigeration system, all refrigeration systems have several basic components. You need to know these components because this is what the entire program is built on when we're talking about refrigeration and air conditioning. We're going to start with the compressor. It's a pump. It pumps or circulates the refrigerant through the system. The compressor converts the low pressure vapor refrigerant to high pressure vapor refrigerant. Notice I'm saying vapor. Compressors do not pump liquids. And as a matter of fact, they will break. Compressors are not meant to run in a vacuum. They don't run under atmospheric pressure. Running a compressor in a vacuum will damage the windings. Refrigerants provide the cooling for these compressors. No refrigerant, the compressor will not cool properly. You have a basic compressor here. You have the oil on the bottom. You might have a piston. You'll have a flapper valve on the suction side. Suction is the inlet side. You'll have a flapper valve on the discharge or the outlet side. Again, suction and discharge. As the piston moves down, it's going to suck gas in through the suction side. And then when it's full, the piston's going to reverse, push up, close the flapper on the suction side to prevent the refrigerant from going the wrong direction, and open the flapper on the discharge side. And that just goes on and on. But in the meantime, we're raising the pressure on that discharge side. The next step in the refrigeration process is the condenser. It rejects the heat from the system. It condenses high pressure vapor into high pressure liquid refrigerant at approximately 30 degrees above the ambient temperature. In this case, we're getting our suction gas from the evaporator. We're coming through the compressor and we're discharging it at 278 psi, which is 200 degrees. Then we're going and we're first dropping our sensible heat. Remember, sensible heat is the basic measurable heat. Okay? We drop from 200 to 125 almost in like the first row of the condenser. We continue at 125 all the way almost through the condenser. What's going on there is we're doing a latent heat change. Remember, latent heat is not measurable, so the temperature is going to stay the same. As we finish up the condenser, we've gone from a vapor to a liquid. We have liquid refrigerant that has now dropped in temperature about a little over halfway through that condenser. We started dropping from 125 to 120 to 110. And we come out of the condenser in our liquid line. The liquid line moves the refrigerant towards the next step in the process, which is the metering device. The metering device controls the flow of refrigerant entering the evaporator. It restricts the flow of refrigerant, which starts the boiling process. It's almost like a resistor in an electrical circuit. One of the types of metering devices is the TXV, which is thermostatic expansion valve. If you think about holding a finger over the end of a garden hose, the hose has high pressure water inside of it. You put your finger over the end of it, all of a sudden you have a spray or a mist. This is a metering device. Your finger's doing the same thing a metering device is doing. The high pressure water in the hose has a higher boiling point because it's under pressure. The low pressure water coming out of the end of the hose has a very low boiling point. So in this example, I have my metering device. We have 278 psi. In front of the metering device on the left side, it's pure liquid. On the right-hand side, we have dropped the pressure through the metering device to 70 psi. We now have a combination of liquid and vapor, which is known as flash gas, 75%, Liquid, 25% vapor. Some of the material will also tell you 80-20. Either one is right. Just know that the majority of it is liquid, but it's at a low pressure. The refrigerant on the left, in the high pressure, has a very high boiling point. The refrigeration on the right, at low pressure, has a lower boiling point, which allows the evaporator coil to work. It absorbs heat from the medium being cooled, evaporates the refrigerant into a 100% low pressure vapor. Remember, as we boil anything, we absorb heat. So the evaporator is absorbing the heat from the actual metal of the evaporator, which then absorbs the heat from the surrounding space. The liquid line that we're talking about carries the high pressure refrigerant from the condenser to the metering device. And this is an evaporator coil. We have room air coming into the coil at 75 degrees. The evaporator coil is 40 degrees because of the low pressure refrigerant that's in that. Okay, the boiling point is 40 degrees, 69 psi for R22. As the air moves across the coil, it's absorbing that heat from the room air into the refrigerant, boiling off the refrigerant, and allowing and basically capturing 20 degrees of heat. The suction line then leaves the evaporator and carries the low pressure vapor from the evaporator to the compressor inlet. And again, notice I've said vapor now. Liquid line has liquid, suction line has vapor. So the entire cycle here, we start at our compressor, we move through our discharge line into our condenser, out of our condenser through our liquid line to the metering device, out of the metering device to the evaporator, and out of the evaporator through the suction line back to the compressor. There's some additional components most of the time you see. For example, the filter dryer. It's a filter that's located on the liquid line. It removes the moisture and any sediment or debris or anything from the system. The dryer material is made out of silica gel or a molecular sieve, which both filter and absorb moisture. The liquid line filter should be replaced any time a system is opened. Special cleanup dryers and suction line core type dryers are usually installed on the systems that are badly contaminated. Make sure you're aware of the direction error on most filter dryers. Most are not bidirectional. In other words, it matters where the arrow is pointing. Remember, the refrigerant is moving out of the condenser to the evaporator. That's the direction the arrow should be pointing. You'll also sometimes see a sight glass. It's a little viewport. It allows the view of the refrigerant flowing in the system. Most of these sight glasses now actually have a moisture indicator on them to let you know if there's any moisture in the system. Do not rely on the sight glass to charge a system. A clear sight glass can mean the system is either empty or full. Don't charge or diagnose the system by sight glass. Always use your gauges. Customers sometimes will call and complain about seeing bubbles in the sight glass, and you'll assume it's a low charge. You cannot rely on that. The only way to diagnose the refrigeration was superheat and subcooling. Refrigerant leaves the compressor as a high pressure vapor in the discharge line. The heat from the compressor and the refrigerant is released into the condenser coil. At this pressure, the boiling point is much higher than the outdoor temperature, and the heat is removed from the refrigerant as it starts to condense to a liquid state. Remember, heat flows from areas of hot to cool. So if my boiling point and my temperature in my condenser is much higher than the surrounding ambient air, the heat's going to naturally flow out of that condenser into the outside air. That's what cools it. Once the refrigerant is 100% liquid, a sensible heat change occurs as the liquid subcools. Subcooling is that sensible heat change. It's measurable because it's sensible. The liquid now carries the refrigerant to the metering device. The refrigerant is forced through the metering device pinhole, and flash gas occurs. Again, 80% liquid, 20% vapor, or 75% liquid, 25% vapor, as the refrigerant exits the metering device into the evaporator coil. Latent heat of evaporization now occurs. Okay, the refrigerant starts to boil off, and remember, as any substance boils, it absorbs heat. The pressure drop allows that refrigerant to be at a colder temperature than the surrounding space. So again, natural heat flow. It comes from the cooler into the evaporator. When the refrigerant is 100% vapor, a sensible heat change occurs that will further heat the vapor. This is superheat. Once the vapor is formed, superheat increases the temperature. The refrigerant returns to the compressor through the suction line. So the refrigeration cycle is once again complete. You'll see in this picture you have the green filter dryer and the sight glass, always in that order. Filter dryer before the sight glass. Superheat, as I said, is a sensible heat change that occurs in approximately the last pass of the tubing in the evaporator coil. It is a sensible heat gain once the latent heat change has been complete. The latent heat change is the liquid changing to a gas. When superheat is normal, the heat transfer in the evaporator coil is working properly. Subcooling is a sensible heat change in the condenser coil following the change of state. When the condenser coil completely condenses the high pressure vapor to a liquid, the temperature should drop an additional 10 to 20 degrees when it enters the liquid line. Again, sensible heat change following the condensing point. Flash gas is right after the metering device. It's 80% liquid, 20% vapor, or 75 and 25. The saturation point is the point at which the refrigerant is 100% liquid or 100% vapor. The liquid saturation point is in the condenser. The vapor saturation point is in the evaporator. It's important to remember that refrigerant is never used up. If it is not in the system when you go looking, there must be a leak. So the refrigeration cycle once more, coming out of the compressor as a vapor, going to the condenser, condenses into a liquid, comes out of the condenser through the liquid line to the filter dryer, then the sight glass, moves on to the metering device, comes out of the metering device as flash gas into the evaporator, begins to boil off. As it becomes a vapor, it moves out of the end of the evaporator and it goes back to the compressor and the cycle starts all over again.